Hello, algebra students. We are looking at Combined Transformations 1 practice, so you want to get your Combined Transformation 1 packet ready. So the first thing we need to do is to graph the original. So we're going to graph the original on the coordinate plane. And we have the point 3, 4. And that's point A. And so we're just going to label that with a capital A. And the point 3, 6. And that would be a capital B. And then the point -2, 4. And that would be point C. So just labeling our original. And then we want to apply the transformation. Now we're going to apply the transformation. It is a translation, and we're given the algebraic rule. And so I'm just going to apply that algebraic rule to each ordered pair. So to each x, I'm going to add 3, and to each y, I'm going to subtract 2. So for the image of A, or A prime, I do 3 plus 3, and that's 6, and 4 minus 2, which gives me 2. So the image of A, or A prime, is the ordered pair 6, 2. And so I would plot that point and include the little apostrophe or image mark. And then on the ordered pair 3, 6, again, x, I'm going to add 3, so that gives me 6. And 6 minus 2 would give me 4 for the y coordinate. And so I'm going to graph the ordered pair for the image of B, which is 6, 4. And so labeling that with a capital B and the image mark apostrophe. And then the ordered pair -2, 4, do the translation of to the right 3. So I'm adding 3, and that's going to give me a +1. And subtracting 2 from the y will give me a +2. So I want to graph the ordered pair 1, 2. And that is C prime, or the image of C. And I connect those and I have my translation. Now it is combined translations or transformations, so we are going to take that translation and then do our next transformation, and we're reflecting over the y-axis. So the rule for reflecting over the y-axis is that the y value stays the same, but the x value becomes its opposite. So I'm going to take the image ordered pairs and apply that rule to it. And so my y values are going to stay the same, and my x values will become the opposite. So my 6 becomes -6, and my 1 becomes a -1. And then I'm going to graph those ordered pairs. So I get the ordered pair -6, 2. And that is a double prime, or the second image. And the ordered pair -6, 4. And that is B double prime, or the second image of B. And -1, 2. And that is C double prime, or the second image of C, and I have created the reflection from the image. Okay, so you can see that I've copied the image or the picture of the coordinate plane and just putting it next to the next question so we can kind of reference that on the screen. And we're finding the lengths of each side for triangle ABC. Now you can see that it's just the plain capital letters. So we are looking at the lengths of the original picture of the original triangle ABC. And basically we're finding the length of AB, and you can see that that is just 2 units long. So I would just put a 2 in there, or 2 units. And for the length of AC, I can count those, 1, 2, 3, 4, 5 units long. And so I just put in 5 units. And then for BC, I have to think about how to do that. We've got a diagonal. And so hopefully realizing that in that diagonal, that is the hypotenuse of a right triangle. And so we use Pythagorean theorem to find that value. And so we can take our 2 legs, 2 squared plus 5 squared will be equal to whatever the hypotenuse is squared. And 2 squared is 4, 5 squared is 25, and again that's going to be equal to the hypotenuse squared. 4 plus 25 is 29, and so c squared is 29. We take the square root of both sides of the equation, and we should get that hypotenuse, or BC, is approximately 5.9. And so that comes out to approximately 5.9 units. Now the next question is asking about the lengths of sides for the second image for the reflection. I know this because of the double prime marks there. And hopefully you're looking at those shapes and you realize that a translation and a reflection do not change the size and shape of the figure, so that our side lengths should remain the same. So A double prime, B double prime should still be 2 units. A double prime, C double prime should still be 5 units. And B double prime, C double prime should still be approximately 5.9 units. Again, the idea being that a translation and a reflection do not change the size of the shape. So what this is emphasizing is that the sides of triangle ABC and triangle A double prime, B double prime, C double prime are congruent. And if the sides are congruent, and that means that the triangles are congruent as well. For the second example of a combined transformation, we again need our original. So we're going to start by graphing our original on the coordinate plane, and this will create a parallelogram. So we have the ordered pair 1, 2, and that's going to be A. And we have the ordered pair 4, 2, and that is our point B. The ordered pair 6, 5 for our point C, and the ordered pair 3, 5 for our point D. And just connecting those, and hopefully you get a parallelogram on yours as well. Then we want to apply a transformation, and the transformation we're looking for is a rotation of 90 degree clockwise. So we want to think about that rule. The 90 degree clockwise is the same as 270 degrees counterclockwise. And so that rule is that you take your original X and Y and you apply the rule where the X and Y switch places and the X becomes its opposite when it's put in the Y coordinate spot. And so let's apply those. So A, I'm going to switch the places of the numbers. So 2 becomes the x coordinate, and then the 1 and taking its opposite, the y coordinate then becomes -1. And for B, it would be 2, -4. And for C, we would get 5, -6. And for D, 5, -3. And then we're going to take those points and plot them on the coordinate plane. And so we will have our 90-degree clockwise rotation. So hopefully looking at our shape resulting in a clockwise turn of 90 degrees. And so let's plot those points. We've got 2, -1, and that would be our point A prime. And then we have 2, -4, and that is our B prime, our first image of B. And we have 5, -6. And that gives us our C prime, and 5, -3. And that gives us our D prime. And we have our 90-degree clockwise rotation of our parallelogram. The next transformation is a dilation. Remember that a dilation is a multiplier, so we have a scale factor of 2 here. So our rule is going to be able to take our rotated ordered pairs, and we want to apply the rule for dilation, which means we are going to multiply both the x and the y value by 2. Since our scale factor is 2. And so our A double prime takes our A prime to -1 and multiplies it by 2. And so we should get 4, -2. And we take the ordered pair 2, -4 and multiply each of those by 2. And we get 4, -8. Multiplying 5, -6 by 2, we get 10, -12, and multiplying 5, -3 by 2, we get 10, -6. And then we want to plot that on our coordinate plane, and we should see a dilation with a scale factor of 2. So I'm going to plot 4, -2, and we get our A double prime, and 4, -8, and we get our B double prime, and then the point 10, -2, -12, sorry. So we go a little off scale there. We're just putting our C double prime down where that would belong. And then we have the ordered pair 10, -6. For our D double prime. And we get our dilated parallelogram. So I'm taking a look at the picture on the coordinate plane and the next question about finding the length of each side of the quadrilateral ABCD. And we're going to show work if we need to. We're around to the nearest tenth. And we have side AB. Now side AB just follows the grid, so that's nice. So we can kind of just count those units. And hopefully you see that that is 3 units long. And side CD, also 3 units long. And then we need to go back to side BC. And side BC is slanted, and so we can't just count them. And we're going to use Pythagorean theorem for a right triangle to find that BC. And so in BC, we have a right triangle with sides of 2 units and a side of 3 units. And then that will give us the length of the hypotenuse, which is side BC. 2 squared is 4. 3 squared is 9. And so we get 13 as our c squared, and taking the square root of each side of the equation, we get about 3.6 units. And so side BC is about 3.6 units. Now side AD, because this is a parallelogram, would be the same. So you certainly could do the Pythagorean theorem work for side AD, but it should come out to be also 3.6 units. Now the next question is finding the lengths of the quadrilateral ABCD prime, or the image of ABCD. And we need to show work if it's necessary. Now, hopefully, this question is really more about what you have remembered about transformations than anything else. And the idea is that our first transformation was a rotation. And so that does not change the shape or size of the figure. And that means that our measures should all be the same. And so we should get 3 units, approximately 3.6 units, 3 units, and again, approximately 3.6 units. So really just asking you to remember which transformations change the size of the shape and which don't. And the idea is that dilation is the only transformation that changes the size of the shape. Now in the next part, we're asked to find the length of each side of the double prime, or the second image, and that was dilated, so those measurements will change. And so we have AB double prime, and we're looking at that, and we can take a look in that picture. And from A to B, we've got 1, 2, 3, 4, 5, 6 units. And hopefully that makes sense, because we were looking at a scale factor of 2. So when we're looking at a 2-dimensional measurement, then, or like a linear measurement, then it should just be multiplied by 2. And so that would be the same for side CD as well. And then for BC, we are looking at, and AD as well, we are looking at a right triangle. I'm going to do AD since that fits on my graph and I can see my right triangle there. And that gives me a length of 1, 2, 3, 4 for one side. And so I can see that that's going to be 4 squared plus a length of 1, 2, 3, 4, 5, 6 for my other side of the right triangle. And I can find the hypotenuse there. And so 4 squared is 16, 6 squared is 36. And so I get 52 is equal to c squared. I take the square root of each side. I get that c is approximately 7.2. And that should make sense to you, as that is 2 times the 3.6 that we got for the original. And our scale factor of our transformation was 2. So you can see that the scale factor also applies to the lengths of the sides. And so considering our last question here on our first part, a quadrilateral ABCD, our original, is congruent to ABC prime. And that is because the sides are all congruent. But quadrilateral ABCD is what compared to quadrilateral double prime ABC, because the sides are what? So they are not congruent because they are not the same size, but in fact they will be similar. So the same shape, but not necessarily the same size, because the sides are proportional. Please remember to take all your questions into your algebra teacher, and we will continue to work on combined transformations in class.